We've got robots that can drive on Mars and build entire cars pretty much on their own. But what if I told you one of the hardest things for a robot to do is this: lacing a shoe? Yeah, it sounds almost silly, but it's actually a massive challenge in robotics. Today, we're going to look at how a brand new framework called GRLR is finally starting to crack the code. And it's a totally fair question, right? It feels a little backwards. We see these amazing robots doing all sorts of complicated things. But lacing a shoe, that's a whole different ballgame. It demands this crazy mix of dexterity, pinpoint precision, and thinking several steps ahead that just pushes modern AI right to the edge. So let's get into what makes this seemingly simple task so incredibly difficult. To really appreciate just how clever the solution is, we first have to wrap our heads around the problem. The researchers call it the dexterity dilemma, and it's basically a perfect storm of robotic challenges, all tied up in one everyday object. Okay, let's break this down. First up, dexterity with precision. The robot isn't grabbing a solid cube, it's trying to control a soft, floppy shoelace. You need millimeter-level accuracy to thread that thing through a tiny little eyelet. Then, there's what they call long horizon robustness. This isn't just one move, it's a whole sequence of moves. If the robot makes one tiny slip up at the beginning, like it fumbles the lace or just misses the hole, the entire attempt is a bust. Game over. And finally, compliant interaction. It's dealing with that wobbly lace and the shoe, which can move and squish around. It's a true Everest of robotic manipulation. So, the researchers behind this GRRL framework had a big realization. The problem wasn't just in the robot's grippers, it was in its brain, specifically in how it was being taught. And it turns out the biggest problem was its teachers, us. And this right here, this is the core insight of the whole project. See, when a human controls a robot arm to show it how to do something this delicate, they're not perfect, not even close. We hesitate, we make tiny little corrections, we might miss the first time and have to try again. The robot, which is trying to learn by watching us, learns all those bad habits. It copies the messiness, not just the successful move. And this slide just nails the difference. On the left, that's the dream, right? The ideal action, a super clean, efficient movement from point A to B. But on the right, well, that's reality. That's the human demonstration. You see those little pauses, the slight overshoots, the moments of hesitation. When you're an AI trying to learn from that, you can't tell what's a necessary part of the motion and what's just a human mistake. So you try to learn it all. This leads to what the researchers call a demonstration and inference mismatch. It's a fancy term, but the idea is simple. The robot learns from messy, imperfect data, but then we expect it to perform with flawless robotic precision. It just doesn't work. It's kind of like trying to learn a piano concerto by listening to a recording filled with hesitations and wrong notes, and then being asked to perform it perfectly on stage. The whole foundation is wobbly. So if humans are flawed teachers, how do you fix it? You can't just find a perfect human to do the demonstrations. Instead, the GRL team came up with a really smart 3-stage training recipe to basically clean up the messy data and then let the robot perfect its skills. And this is it, this beautiful 3-step process. First, they filter out all the human mistakes. Second, they augment the good data to get more bang for their buck. And finally, they let the robot reinforce its own learning through actual practice. Let's dig into each of these. Okay, step 1, filter. This is so cool. They train a second AI, which they call a critic, to just watch all the human demonstrations. By seeing what leads to success and what leads to failure, this critic gets really good at spotting what making progress actually looks like. So it goes through all the training data, second by second, and filters out anything that looks like a hesitation or a mistake, anything that isn't actively moving toward the goal. What you're left with is just the clean, effective parts of the demonstration. Step 2 is augment, and this is one of those brilliantly simple ideas. To make the robot smarter without spending ages collecting more data, they just use a mirror. They take a successful recording of the robot lacing the left side of the shoe, and they digitally flip everything. The camera feed, the arm movements, even the text command from left hole to right hole. And boom! Instantly, the robot has a perfect example of how to do the right side. You've basically doubled your useful training data for free, which helps the robot generalize what it's learned way better. And that brings us to the final crucial step, reinforce. So after learning from all that clean, mirrored data, the robot's pretty good, but it's not a master yet. To get that last 10% of precision, it just starts practicing on its own in the real world. This is reinforcement learning. It learns from trial and error. Every time it gets it right, that behavior is reinforced. Every time it fails, it learns what not to do. This is the step that really closes that mismatch we talked about, fine-tuning its skills based on what actually works in the real world. So you've got the three-part recipe: filter, augment, and reinforce. It sounds great on paper, but the proof is in the pudding. Did it actually work? Let's take a look at the results.
And the answer is, oh yeah, it worked, a whopping 83.3% of the time. After going through the full GRL training, the robot could successfully lace the shoe. That is a massive deal, making it the very first system of its kind to autonomously nail such a complex, delicate task with this kind of reliability.
This chart really tells the whole story. Look at that bar on the left. The base model, the one trained the old-fashioned way on raw, messy human data, it succeeded less than half the time. A coin flip, basically. But just by filtering and augmenting that data, steps 1 and 2, the success rate jumps to almost 73%. But it's that final step, the online reinforcement, where the robot practices on its own, that pushes it over the 80% finish line and turns it into a true expert. And maybe the most impressive part is that we're not just talking about success under perfect lab conditions. This robot shows incredible robustness. It's smart. If it drops the lace, it knows how to pick it back up. If it misses the eyelet, it tries again. It'll even shift the shoe around for a better angle or re-grip the lace if it doesn't have it just right. This is not a machine just blindly repeating a program. It's an agent that is actively problem-solving in real time. So, what's the big takeaway from all this? I mean, this is obviously not just a party trick for a robot. The implications here are actually much, much bigger. Because what we're really seeing here isn't about shoes at all. It's about a new way to take a capable, general-purpose AI and turn it into a high-performance, reliable specialist for a really tough job. Think of the GRL framework as a blueprint. It's a recipe that other researchers can now use for other incredibly complex and delicate tasks. We're talking about things like assisting in surgery or assembling tiny, intricate electronics. This is a potential pathway for creating robots that we can actually trust to do jobs that require true, reliable expertise. And that really just leaves us with one final fascinating thought. For years and years, a task like lacing a shoe seemed almost impossibly out of reach for a robot learning on its own. Now that we have a recipe for creating these kinds of specialists, it really makes you wonder, what's the next impossible task that's about to become possible?